Okay, now I can start. So let me recall first some notation from the previous lecture. We consider the Young graph. Oh, some problem, just a minute. Okay. So let's consider the Young graph. The Young graph. And I recall the notation for the path space. The path space, which can be viewed as the set of infinite Young tableau, standard Young tableau. Young tableau. So I recall the picture, we have graph. It is infinite. And we consider some infinite path which goes up in my picture. And the set of all paths is the set of Young tableau, standard Young tableau. And what next? I recall that this is a compact topological space. Compact topological space. And the topology, the base of a topology, is formed by elementary cylinders. I recall what is a cylinder, so we take some finite path, and next all possible continuations. Such a set is called an elementary cylinder, and they form the base of a topology. And also they generate the sigma algebra of Borel sets. And now we consider the set of Gibbs measures on the space. And I briefly recall its definition. These are probability measures. With some special property, the Gibbs property or centrality property in a different terminology, which means as follows. Given, so consider the levels of our graph and fix some level, maybe just drag some level, some vertex lambda, and take all finite paths which terminate at this vertex. And given such a path, we consider the corresponding elementary cylinder set. And the condition is as follows. condition is as follows. So given such a finite path, and this is a corresponding cylinder set. The condition is that the mass of this cylinder is elementary. Depends on lambda only, but not on the choice of tau. So any possible finite paths which terminate at this vertex gives the same mass. Okay. So this is the Gibbs property. And I proved the following result, that there is a bijection. There is a bijection between Gibbs measures and non-negative harmonic functions. Let's say M is my notation for a Gibbs measure, and phi is harmonic functions on the set of Young diagrams, normalized by the condition that the value at the empty diagram is equal to 1, which corresponds to the normalization of our measures. So we have this bijection. What I proved, I also proved that we have some examples of M's, or which is the same of phi's. They are as follows. The fundamental example is the Plancherel Gibbs measure, or Plancherel harmonic function. Plancherel is defined as follows. The value is equal to the dimension lambda divided by the size of lambda factorial. And a more complicated example is the Z measures of Z harmonic functions. It's defined as follows. We fix two complex numbers, Z and Z prime, which assume for simplicity that they are not real. And then the harmonic function is defined as follows. First, we take the product over the boxes of our diagram, Z plus the content of the box, Z prime plus the content. Next, some normalization constant, which is equal to Z prime per Hammer symbol. I assume as usual that N is the size, and times the Plancherel factor, which is the dimension, divided by factorial. And this function is harmonic. It is harmonic. It is harmonic. It is normalized. But we also want the positivity, non-negativity, and non-negativity is achieved a sufficient condition is as follows, that Z and Z prime are complex conjugate. It's enough. There is one more possibility if they are real, both are real, and are contained in some interval between two consecutive integers. This also gives us the required positivity. And I proved the harmonicity of this function. It's not obvious. It is proved. I proved it using the formalism of Kerr interlacing coordinates. Now, I would like to discuss the following problem. How to describe all Gibbs measures. Which is the same, all phi's which are non-negative, normalized, and harmonic. And there is a nice solution. First of all, it consists of two parts. So first, this is sub-problem. Describe all specialization of our algebra of symmetric function. So I recall that a specialization in an algebra homomorphism or specializations which are positive. I will say positive meaning non-negative. Non-negative. I will always use this adjective positive in the sense non-negative. Positive and satisfying the condition that I need some notation. What I want to say? Psi. And such that psi of is equal to 1. So I recall that this is the simplest Schur function which corresponds to the one-box diagram, which is the same with H1 or I have some problem about just a moment. Just a moment, what happens? Moment. Just a moment, I will try again. No, it does not work. I have to restart. Excuse me. Some technical problem. No. Okay. Just wait a minute. Okay. So I resume. Too many problems. I'm sorry. So I resume, but it is the same. So this is the simplest homogeneous symmetric function. So I repeat that I want to describe all specialization, that is multiplicative linear functions. And I claim that if it is positive, positive means that the value on any sure function is non-negative. This is very important. So I claim that if you have, we have such specialization, psi, that we have also harmonic function with all the properties. This is easy to see, indeed. We just given psi, we set phi lambda is equal to, and all desired properties are satisfied. Indeed, we have non-negativity because we have non-negativity here. And we have normalization. This is because we have this condition. And finally, we have harmonicity. Because what we know, we write that is equal to the sum over all mu, which is over lambda, and just then apply psi to both sides. And then we get that this is because this is a homomorphism, it's multiplicative, and we get, but we know by assumption that this is equal to 1, and in this way we get harmonicity. So the first step is classify specialization. Not any. It's not true that any harmonic function is given by this construction. is wrong. But this is some very special and particular case of harmonic functions. How to find them. And this is the result, which is called Thoma theorem in equivalent formulation. Elmar Thoma was a German mathematician, and he proved a remarkable result. Mathematische Zeitschrift, which is as follows: to specify a specialization, it's enough to indicate and sufficient to indicate its value on any set of generators of our algebra, and take the generators. And Thomas' theorem says that positive and normalized specialization are given as follows. There are infinitely many parameters, alphas, which are non-negative. It's denoted as follows: the string of alpha parameters. Another set of beta parameters, which are also some real and non-negative numbers. And subject to the only condition that the sum of the alphas plus the sum of the betas does not exceed 1. And given such pairs of infinite sequences of parameters, we define a specialization as follows. The value at the h function is given as follows. Is defined. It's convenient to use generating series. So we write sum over n from 1 to infinity. So this is the generating series, and the formula is as follows. I will write and then I will explain what is this. What is gamma? Gamma is by definition the difference between 1 and the sum of alphas and betas. This is some quantity which is non-negative. And so what is obvious from this formula? What is obvious? Obvious is that the value on h1 is equal to 1. Why it is? Because we need to extract the coefficient from this expression. expression. And it's easy to see that this coefficient of degree 1, it is equal to the sum of the alphas which come from denominator plus the sum of the betas which come from the numerator and plus gamma which come from the expansion of the exponent. And this is equal to 1, exactly, to 1 by the very definition of gamma. So one of our conditions is satisfied. So this is trivial. What is highly non-trivial is y, not highly, but nevertheless, y it's positive. Why it's positive. The idea is follows. How to prove this? So we want to prove positivity. That is y. Y. So the idea, a beautiful idea, it's due to curve. This is, I will call it curve mixing construction. Mixing construction. I will explain what it is. The idea is to use the coproduct, the co-multiplication in the algebra of symmetric function. I recall the definition. The tensor square, tensor product, coproduct. And this is an algebra homomorphism. In algebra homomorphism, this is important for us. And the definition is simple. Namely, if you have some symmetric function, we just split our set of variables into parts. And the result is separately symmetric in the x's and in the y's. This gives us this, okay? And we have structure constants of our coproduct. Namely, if we apply a coproduct to a Schur function, then we get some expansion in the products of two Schur functions on the right. So this can be written as follows. And what is important, that this is a fact which I proved in one of the previous lectures, that these constants are the same as the Littlewood-Richardson constants, which are the structure constants for the multiplication. And to simplify my exposition, I will assume that we already know that these numbers are non-negative. In fact, it's not necessary to use, we will see, but to simplify things, let's assume that we know this. In fact, these are non-negative integers, but I did not prove it. So let's assume that we know. So we have this okay. Now the mixing construction, what it gives us. It's a way to produce non-negative specialization from simplest ones. So assume that we have the following data. So assume we have two which are positive specialization. Which satisfy our properties. And we want to build from them some new specialization with the same properties, with similar properties. And our construction will also depend on some parameter. On some parameter, let's call it's T. So I want to produce a new, that's denoted as follows. Psi. And I assume that T is a real number contained in the unit interval, in the closed unit interval. I also need some extra notation. How to, no, I'm sorry, I want to change my notation for this parameter. I'm sorry, let's write it as R. It will be better. Let's denote by R, AR, automorphism. Automorphism. Such that is defined just as follows: f, some homogeneous sum function, I will write a little bit informal way. It just means if f is homogeneous of some degree n, then f is multiplication by this number. Okay. So if f is homogeneous, if you multiply all the arguments by r, we get this factor in front. So this is automorphism. It's rather.
Do we consider SIM as real algebra? Because on the first lecture we negotiated that we will consider SIM as Q-algebra, and it seems then in this case R should be also rational, or no?
No, it's not necessary. Let's take as okay. Let's take as the base field the field of real numbers. Real numbers, not Q, but real numbers. In all this story, it's much more convenient to abandon the base field Q and take the real numbers. Okay. So now there is no problem. Now I will describe this construction. This construction is as follows. So we want to define define psi, given this is my notation, it's as follows. We defined it as a composition on several maps. So psi should be some homomorphism into the real numbers. How to get it? So we take our algebra symmetric functions. First of all, we take the coproduct. And next, we apply the automorphism, which is as follows. We take a R tensor A1 minus R. So this is correct because, not correct, I mean that 1 minus R is also a real number from the same interval. And in this way, we get next we apply and this gives us some homomorphism into R. Okay. And this is a homomorphism because it is a composition. We know that this is algebra homomorphism. This is application of automorphisms, and this is also homomorphism, so it's correct. What next? What next? We want to prove that this is a specialization satisfying our properties. So what we need to verify, that it's equal to 1 on H1. Okay, so what happens with H1? What happens with it? Under the first row, we get this. Which is easy to verify. This is the same as P1, separation of variables just gives us this. Application of this gives us maybe. So okay. And after applying the last row, we just get so what we have used? We have used the most important fact that this is a homomorphism. This is a homomorphism. And what next? We want to verify the positivity. Positivity. And this is as follows. This follows from the fact that our structure constants are non-negative. Why? Because we have that lambda is mapped onto the sum into the sum. Okay. So this row, this step, I mean, just add some positive factors. R. Okay, one can write it. Then we get mu and mu. Okay. And then we get sum. And all the terms are non-negative here. So we get non-negativity. So we see that if you have some, we have some operation, some good operation, which allows us to construct new specialization with our properties from some existing ones. Now we apply this. The final step is to apply this procedure. Apply this. We need some initial specializations, some quite trivial ones, and they are as follows. Like this, the simplest specialization. They are as follows. And maybe some notation. Okay, so psi plus. Its value is equal to 1 if lambda is a one-row diagram and 0 otherwise. And psi minus is defined in a similar way. It's equal 1 for one column diagrams and 0 otherwise. It's trivial to see that these are good specialization, which just means as follows: the psi plus, they sense it sends. Okay, maybe it's one can explain it more easily, as follows. Why? It's a specialization. It's a specialization because it's defined as follows. n. And then one can prove easily, using, say, the Jacobi-Trudi, if you wish, that we have this property. We have this property. And harmonicity also follows easily, because adding a box, we can add only the box in the same row, okay? And there is no sum. So what I would like, we have to prove that, okay, but in any way, one can, if we defined a specialization can be defined by this property, and then one can prove that it satisfies this equality, this property using the Jacobi-Trudi. In terms of Gibbs measures, the corresponding Gibbs measure is just the delta measure, which is concentrated on a single path, which goes along one row diagram. So we have empty, then we have one row, then we have one row with two boxes, and so on. It's easy to see that it is a Gibbs measure. And in terms of specialization, it's just this one. And by symmetry, by applying the duality map omega, we get, by symmetry, we get this one. And now we apply the mixing procedure. We apply the mixing procedure. So we can take some we can apply it several times. So we can generalize a little bit our mixing construction. I mean, as follows, a little generalization. So if you have some finite numbers of specialization, we can construct, and some m tuple of real numbers, which are all non-negative, and sum to 1. We can define their mixing. Maybe it's better to write actually in a little bit different way, the mixing parameters. I mean that we apply the same procedure. We can take the iterated coproduct. So we apply just the same procedure, only we take which send to the m-fold product. And then we apply our automorphisms. And then we apply the product of this size. And we get the result. Okay. So what happens now? First, consider some alphas. So I take finitely many alphas. So we take alpha is such that the sum of alphas. So even, okay, so the sum is equal to 1. Actually, why I write this inequality? This is because our operation is symmetric. We can permute this specialization together with the mixing parameters, and nothing changes. Okay. This holds because our coproduct is symmetric. So we can permute them, and we can arrange for simplicity the mixing parameters in the weakly descending order. And now I take as these mixing parameters the alphas. So I take plus psi plus with these parameters. And what we get. And I claim that this gives us, denote it as psi. And I claim that what I would like, maybe it's better to introduce the notation. H of t is the generating function, or maybe z, because I used the letter z, sorry. Z is the generating function I recall that H0 is equal to 1. So this is the generating series. And given a specialization, psi, right, okay. And what next? What next? What next? The important fact is as follows. Fact is that H of Z is a so-called group like, formally, group-like element. Group-like element. What does this mean? This means that how to understand this? This means that just that, no, I'm sorry. Is it correct? No, it's correct. It's correct, sorry. It's correct. This is just the, so what is this? We just to have is by definition this series. Okay. And what we have to prove? We have to prove that we use the fact the sum of non-negative integers k and l, which sum to n. This is a finite sum. And why it's so? Just apply the definition of the h function, and look what happens if you split the set of variables into two parts. And in this way, we get just this, because Hn is simply the sum of all monomials of total degree n. And applying this, if you split our variables, we just get this very easily. And using this, we get this property. And now it's easy to see what happens after our mixing. So what happens under mixing? I recall that specialization is uniquely determined by its value on the h functions. And so it's convenient to use this form as the definition. So the left-hand side, focus on the left-hand side. So we want to understand what happens if you have two parameters, and we apply it to what happens. And the result is as follows. We see that the result is as follows. You have and assume that more generally, we have and we apply this HT, and the result what we get is the product why it's so. This is so because our automorphism, which I recall is just it acts as multiplication by in degree n, it just corresponds to this operation in the generating function. Because if you look here, if we multiply our formal parameter z by some number r, which produces r in raised to power n, which is just what we want here. And now we apply, so we apply this. First, we apply it to plus and with parameters alpha m. And what we get, we need to understand what happens with psi plus of h of z. This is very easy to see. It is just okay. Why? Because this is 1 plus z plus z squared and so on. And this just gives us psi plus, which equals to 1 for any powers, okay? And after this mixing, we get a more complicated function. We get just this one. Okay. Now we can also use psi minus. Use psi minus. What is this one? I claim that it's equal to 1 plus z. 1 plus z. Why it is? One reason is as follows. We have to compute the values on the h function, but we know that psi minus as harmonic functions is concentrated on one columns diagrams. And the only one row diagram, which is also one column diagram, is the simplest one, this one. Another possibility is to use the duality or use the omega, which maps the h functions to the e function, elementary symmetric functions. Now we can mix up, we can mix up some number of psi plus and some number of psi minus with parameters alphas, A and betas, any numbers. Assume that the sum, okay, one can take, say, the same number, does not matter because we can take the zero parameters, which gives nothing. So we can always assume that we have equally many alphas and betas. And we assume that they sum to 1. And mixing up all this gives us the following. The following result. A finite product. But we want infinite product, and we want also drop this condition. Drop the condition that the sum is exactly equal to 1. How to do this? By continuity. By continuity. How to do this? Introduce the notation, the Thoma simplex. Thoma simplex. denoted as omega. This is a subset. This is a subset in R infinity times R infinity, which is just the set, our set of alpha and betas, where alpha is as before, non-negative, beta is subject to similar condition, and the sum does not exceed 1. So the set of our parameters is denoted as omega, and it is called the simplex. I will explain later on why it is really a simplex. It is a simplex because we can take why it is simplex. This is an infinite dimensional simplex because we can take as a new set of coordinates. We can take this one, and this is a little bit artificial, but it works. All these numbers are non-negative, and they sum to so we if you want to get rid from these inequalities, we just pass to new coordinates, which can be arbitrary non-negative real numbers, and likewise for the betas and at gamma. And all these parameters, all these new parameters are non-negative real numbers, infinitely many, which sum to 1. So this is an infinite dimensional simplex. So this is why it is called simplex. What next? We want to use the topology, topology in omega. The topology is induced by the product topology, is induced by the product topology. Product topology of the space, of a product space, the infinite product space, we can write it as informally. A product of infinitely many, but in fact, because of this condition, we can simply take, take the unit segment to power to infinity, because all our coordinates lie inside this interval, closed interval. So it's enough to take only it. And this is nice because the closed interval is a compact space, and this product is, in the product topology, is also a compact space. And now, what I would like to say, that consider the set finite part, which means that finitely many, zero alpha betas, and the sum is exactly equal to 1. And I claim that this claim that is dense. omega. Why it is? What means informally? What is the topology? If you have some point, you have some point in this space, so some double collection of alphas and betas, and another point is close to it if some prescribed by finite number of coordinates is closed only, and the rest does not matter. The larger is this set of prescribed coordinates on which we focus. The smaller is the neighborhood, the points are closer to each other. And from this description, it's already clear that any point of our space omega, any point with many, possibly infinitely many coordinates, which and such that their sum is only is not equal exactly to 1, can be approximated by this by points from this subset. So it's dense. It's dense. And the next remark, so we have some map. We constructed a map. We constructed a map from this set to specializations psi with properties that we need. And I claim now, with some exercise, I want to leave it as exercise, that this map is continuous. It's continuous in the topology. This is a fine property. Fine property. It's continuous. And this map can be extended by continuity to the whole. This extends by continuity to the whole space. The whole space, which from this relatively small subset. And so we can generalize this formula first by taking possibly infinitely many parameters, and next, which is a little bit finer properties, we can also get this. A way to get this as a limit point. How to get, for instance, how to get exactly, in particular, we want to get this one. And this corresponds to gamma equal to 1. So this just means this one. How to get it as a limit? Take a limit. Of, say, and all the other parameters are equal to 0. Okay, so what we get then? We get this function. and as n goes to infinity, which gives us this one. Or equally well, we can take this one. The same way we get this one. So this is an example which, and one can verify that this yes, example just corresponds to a Plancherel case. It's just a Plancherel specialization. Okay. So what I tried to explain is exactly the Thoma theorem. The Thoma theorem. So what I explained is how to obtain this formula, how to prove that this formula gives us positive specializations. I did not prove that this list of positive specializations, which are indexed by the alpha and beta parameters, is exhaustive. I did not prove that the result is complete. It's not so easy. I will not prove it. But in fact, it is exactly all positive specializations normalized by the condition that but the final result is as follows. Final result. Final result. Final result. So we have, so what we have for any betas from the Thoma simplex, it produces some specialization, and which is the same as some harmonic function, such that harmonic function is the value on the Young diagram is equal to psi, the value on the Schur function. And a general form is as follows. General form. Form of positive normalized harmonic function, and hence of a Gibbs measure. Psi is follows. Maybe it's better to introduce some extra notation. I want to, because I have omega, capital omega, its point is small omega. Small omega is just this pair. And gamma is determined by the alpha and beta, so it's not an independent parameters. So the idea is as follows. Let's P be any probability measure on omega. It's a compact space, a compact topological space, hence it has a canonical sigma algebra of Borel sets generated by the topology. So take an arbitrary probability measure and integrate our, I will write instead of alpha betas, I will write small omega and take the integral of our space. And it's easy to see that it's again the harmonic function. Why? Because the very definition of harmonic function involves only some additive condition. Additive condition. We have an additive condition. So if you have some number of some collection of harmonic functions, the convex linear combination, that is a linear combination with non-negative coefficients which sum to 1. It satisfies all our conditions: positivity, harmonicity, and normalization. And probability measures just appears as the result of taking limits of finite convex combination. Any probability measure on a good space can be obtained as the weak limit of finite atomic measures, which is concentrated on finitely many points and gives them some non-negative weights, purely atomic measures. And so we can get in this way any probability measures. So this explains why this formula should work. And in fact, it gives us all the possible harmonic functions. So the general picture is as follows. We have some infinite dimensional but still good space, which is compact space, and geometrically it is an infinitely dimensional simplex. It is a compact space, a good space. We can take any probability measure, and these are the data for the parameters, complicated parameters, functional parameters. So one can say even a little bit more, because we have first some countably many continuous parameters, and next the measures on these parameters. Nevertheless, it's quite a reasonable answer. And this gives us all harmonic functions and hence all Gibbs measures. Okay. So I would like to stop at this moment. I would like only say that this result has also representation theoretic meaning, because it produces all possible characters in some sense of an infinite symmetric group. So this is a result which was initially the aim of Elmar Thoma. He explained what a character of infinite symmetric group means, and then he proved this result. So let me stop at this moment and